Assalamu alaikum everyone, and welcome to another session for EEE 6307. So let's continue from the last class where we ended. So the topic that we took into consideration in the last class was that of the dynamic modeling for the three-phase induction machine, which is one of the mostly used three-phase dynamic load in the industries all around the world. So we started the dynamic modeling topic with some of the basic or the salient features associated with the induction machine, that is the three-phase induction machine. So at the beginning, I tried to point out some of the main differences between the three-phase induction machine and the three-phase synchronous machine. One of the reason is that because I have already covered the detail of the modeling on the three-phase synchronous machine. So after that, I continued with the schematic of the three-phase induction machine diagram. So there are some similarities between the three-phase induction machine and the three-phase synchronous machine. Specifically in the stator construction part, there is no major difference between these two machines. So like the three-phase synchronous machine, here also we are assuming that we have a direct axis or the direct axis or the D axis in short, and along with that we have a quadrature axis, or in short that is called as Q axis. The current directions, like the synchronous machine case, here also we are assuming the dot representation means the current is flowing out of the page, and the cross means the current is going into the page. The small ABC, these were the representatives for the stator quantities, three-phase stator quantities, and the capital ABCs were the representative for the rotor quantities. So unlike the synchronous machine, in this case, especially if this is an own rotor type, so we will be having three physical set of coils. So in the rotor part, we will be having phase A, phase B, and phase C coils as shown in the diagram. So you can clearly see that the small B axis and the small A axis and the small C axis, they belong to the stator coils. And if you look closely into the direction of current flow through the coils, so you can clearly see that all these three phases are carrying current into the coils. So that is basically the motor convention, means we are actually supplying three-phase power into the three-phase balanced set of windings in the stator coil. Accordingly, because at the very beginning the rotor would be stationary, so there will be some relative speed due to the fact that once we supply the three-phase balanced voltages in the stator three-phase coils, so there will be one rotating magnetic field. The creation of the rotating magnetic field that will be available in the air gap, and the rotor coil will sense that there is a change in magnetic field because of their speed being zero at the very beginning. So the rotor coils are stationary at the very beginning of the operation of the induction machine. So because of that relative speed between the rotor actual speed and the rotating magnetic field available in the air gap, there will be some induced voltage in these coils. So the capital A prime, the capital B prime, and the capital C prime, these are the representatives for the rotor coils. So once they have the induced voltage, and as per the construction of the one rotor induction machine, we have to either use the resistor three-phase resistive elements in three different phases, of course in a balanced manner to keep things balanced, but ultimately we have to short out the ends. So either you can go for some finite resistance, or you can simply short circuit the three-phase coils available in the rotor circuit. The reason is that we actually want the current to be flown in the rotor coils. So once the rotor coil carries that current or produces that current due to the induced EMF on them, there is a rotor magnetic field. And ultimately, due to the Lenz's law, we have studied these in our undergrad level, that the rotor would start to move in the same direction as the rotating magnetic field is moving in the air gap. Ultimately, once the rotor starts to move, this speed difference, if we denote the speeds for the RMF, so let's say the rotating magnetic field would be rotating at the synchronous speed omega s or omega synchronous, and the rotor itself would be rotating at omega r. So there will be some relative speed, omega synchronous, or let's say omega s, in short, omega s minus omega r. So this would be the relative speed. And because of this, these rotor coils would be getting, finally, this rotor coil would be getting some induced current. At a steady state, once the rotor reaches the steady state speed, that means the omega r reaches some steady state value, then based on this difference, that is slip speed, based on this difference, there will be the induced current under a steady state condition. And if it is a motor operation, then of course omega s would be always greater than omega r. So then what we did, we assumed some positional notation. So let's say we assume that we have a set of d axis and q axis coil which are coupled. That means the speed at which the d axis is moving, at the same speed the q axis would be moving, and we assume that they belong to this speed, that is the omega s. So the dq axis frame, this is actually rotating at synchronous speed. The stator A coil, B coil, A coil, and C coil, they are actually stationary. So these three don't have any speed. They are actually fixed at their position. Space-wise, they are fixed. However, the rotor A axis, the rotor B axis, and the rotor C axis, they are moving at a certain speed, omega r. So we have actually three different speeds. The dq axis moving at omega synchronous, the rotor axis moving at omega r, the stationary axis, that is the stator's coils, are stationary, omega equals to 0. So we have three different speeds to be deal with. Then we started with some of the notations, that is theta and theta r. So theta was the angle between the stator A axis and the rotor A axis. So specifically, this is the theta. We talked about the theta. This is the angular difference, or the angular position difference between the rotor A axis and the stator A axis. So because the rotor A axis would be moving at a certain speed, omega r, and the stator A axis would be stationary, that means with respect to time, this distance theta would be changing. And that can be represented as a function of time in this manner, theta equals to omega r into t. The second angular difference was denoted by theta r, and that is the angle between the synchronously rotating d axis and the actual rotor frame speed, omega r. And we finally introduced this term, slip. S is the slip, and that is omega s minus omega r divided by omega s, where omega s is nothing but the synchronous speed. So these are the things that we covered in the last class. Then we continued with our discussion. We completed this slide also, where we showed some of the basic relationships between the theta and omega r, and the derivative of the first time derivative of theta r. And we saw that, well, in that manner, we actually can establish the relationship between omega s, the slip, and the first time derivative of theta r. So these are some of the relationship that would come handy later on in our derivation. Then we started with the stator winding voltage, and these are three phase. So we said that there is a basic difference between the expression between the stator winding voltage for the wound rotor induction machine and the three-phase synchronous machine, specifically because we are considering that this wound rotor induction machine would be an example of a load. So the current would be actually coming into the terminals. So these currents, IA, IB, and IC, these would be actually flowing from the source end to the load end. So that means current would be coming into these coils, coil A, stator, coil B, stator, and coil C, stator. And because the current is coming into the load, so that's why there is a positive sign. Okay, so this voltage drop, RSIA, RSIB, and RSIC would be having a plus sign, unlike the synchronous machine. In the synchronous machine, we considered mainly the synchronous generator modeling. So we saw in that case that there were minus signs in all these three cases. Okay, so this is a difference in the representation of the stator winding voltage. Other than that, all are same. So this is simply KVL for coil A, this is KVL for coil B, stator, and this is KVL for coil C, stator. Similarly, the rotor winding voltage, now we use the V capital A, V capital B, and V capital C. Other than that, we have a simple difference. This RS in the stator winding voltage, this is the stator winding resistance. And this RR, this is the rotor winding resistance. Other than that, simply we have replaced the small a, B, and C by the capital A, B, and C for the representation of the rotor winding voltage. Okay, then we talked about this stator winding flux linkage. Detailed discussion was given in the last class. Similarly, the rotor winding flux linkage, detailed discussion was given in the last class. I'm not going to repeat it again. I'm not going to repeat it. There was some salient features, especially this part over here, because these lambda A, lambda B, lambda C, these are nothing but the stator flux linkage expressions. So in short, these are lambda stator, three phase. This is rotor current, I rotor, three phase. This is I stator. So this inductance matrix, this is simply relating the stator to stator quantities. So you can also write it as LSS. And this matrix here, 3 by 3 matrix over here, this is relating the stator flux linkage and the rotor current flows, current flowing through the rotor coils. So you can also call it L stator to rotor. And interestingly, in this case, we will see that LSR is exactly the same as LRS in this case. So this is now lambda rotor, the leftmost column is the lambda rotor, that's the rotor flux linkage expression. So this is lambda rotor. This is again I stator. This is I rotor. So this should be L rotor to stator. So ARS, and this is simply rotor to rotor. So this should be LRR. And interestingly, again, this LRS is simply the LSR. No difference. Okay. So this is where we stopped in the last class. So let's continue from here, from the next slide. So like the synchronous machine modeling, at this point, what we did for the synchronous machine modeling was to introduce actually this concept of Parkes transformation. Okay. Okay. So this is the transformation that we actually used for the transformation from the ABC quantities to the DQ0 frame in case of the synchronous machine discussion. So similarly here, already we have seen the stator winding flux linkage that they are in the ABC frame. The rotor winding flux linkage, they are in the ABC frame. The rotor winding voltage expression, it is in the ABC frame, as well as the stator winding voltage expression, it is also in the ABC frame. So, and we can also see that these flux linkage expressions, lambda A, lambda B, lambda C, when there is some mutual element, remember this block over here, this block is the mutual flux link, mutual inductance elements. Expression of that depends on the rotor position, theta, okay, angular position, theta. Similarly, the rotor winding flux linkage, we can also see that this mutual inductance part, this block 3 by 3 here, also depends on the theta. So one benefit or advantage that we achieved by introducing the Parkes transformation in case of the synchronous machine is we got rid of this theta dependency. Okay, so lambda A, lambda B, lambda C, ultimately with the use of this Parkes transformation, we were able to get rid of this theta dependency for our flux linkage and the voltage expressions ultimately. So with the same target, with the same motivation, we will again try to implement the Parkes transformation, and we will see what benefits we are going to get ultimately. But again, because this is an induction machine, so there would be some differences. So before I introduce the differences, let me first focus on what is the similarity. So in the first matrix, in equation 6a, we can see the Parkes transformation being mentioned here as TDQ0S. Okay. So we were already familiar with TDQ0. So what is that S specifically? So T dq0 is nothing but the transformation matrix itself. And the S here means it is used for the stator quantities. So this specific parse transformation over here is only used for transforming the stator quantities. So that means you are transforming from stator ABC to some dq0 frame. Okay. So there is basically no big difference between this TDQ0S and whatever TDQ0 we used for the synchronous machine. Okay, so you can clearly see that there is a 2/3, there is a half over there, and all the other elements are exactly same as we used for the synchronous machine parse transformation. One thing I should mention here that in the case of synchronous machine, we used actually the symbols K1 and K2. And in that case, we mentioned the specific benefits or advantages for each case. So there were two choices for K1 and K2. And probably here, we are only using one of those, okay? So there's nothing new, just we have fixed the K1 and K2 values to a certain set of values, okay? In the case of synchronous machine, they were arbitrary. They could be chosen from any of these. So they could be chosen from any of these two, either K1. So the K1 was in K2. In this case, we are using the combination of 2/3 and 1/2. And probably there was another combination, okay? K2 was probably 1/2, something like this. So in this case, we are using this one. But another choice could be this one, okay? So this is the same Parks transformation matrix for that we used for the synchronous machine. Okay. So what it actually says, if we look at this speed of the Parks transformation matrix, the speed used or the angular speed quantity used for the Parks transformation for transforming the stator quantities ABC into the dq0 frame, we are using one speed quantity omega s. Okay. So now let us look at the speed of these two frames closely. What is the speed of the stator quantities? As we already mentioned, it is 0. Okay. ABC frame, speed of the ABC frame. That means the stator coils, coil A, coil B, coil C. Physically, they are present in the stator and they are fixed in space. So if we want to represent their speed, we should use the term 0. What is the speed of the dq0 frame? It is omega s. The speed of the dq0 frame is omega s. If you just go back a few slides, roll back a few slides, then you can see that this ABC frame is rotating at 0. So it is stationary actually. A axis, B axis, and C axis, they are clearly unmoved. Okay, so this omega is actually 0. What is the speed of the dq axis? Omega s. So what is the relative speed between d axis and the stator axis? Omega s minus 0, and the resulting speed is omega s. So basically, in the Parks transformation, we are in the elements itself, within the elements, we are using the speed term, which is nothing but the relative speed between the two frames of reference. One frame of reference is the stator frame, whose speed is 0. Another frame of reference is the d-axis, whose speed is omega s. So you are moving from 0 to omega s, from 0 to omega s. We are transforming ABC stator to dq0. So the relative speed is omega s. So that omega s is actually coming in the matrix representation for the Parks transformation in the T dq0s. Here. Okay. So this is the place. Everywhere you will see omega s, everywhere omega s. Okay. So if there is any speed, that would be omega s, nothing else. Now, in case of synchronous machine, we only had these two speeds. Okay. The rotor itself, in case of synchronous machine, the rotor itself in a steady state This was the rotor, this was the coil, and this was the d-axis. So the rotor as well as the d-axis both were moving at synchronous speed because it was a synchronous machine. So under steady state, both of their speed was omega s. Stator speed was 0. So there were only 2 speeds involved in case of synchronous machine, synchronous generator, let's say. In case of wound rotor induction machine, there are 3 speeds. One is the speed of the DQ axis, that is synchronous omega s. One is the speed of the stator coils ABC, that is 0, and one is the rotor coils A, B, C, that is omega r. So now we have the rotor quantities in its own ABC frame, which are to be transformed into the DQ reference frame. So the DQ reference frame is moving at omega s. The rotor quantities which are to be transformed into the to the DQ reference frame, which is moving at omega s. The rotor quantity is moving at omega r. So what is the relative speed? Omega s minus omega r. So the speed terms that would appear in the TDQ0 transformation for the rotor are, R stands for rotor here. So in here, all the quantities that you will see in the speed term would be the relative speed between the DQ0 reference frame speed, that is omega s, minus the rotor actual speed, that is omega r. So here you will see that omega s minus omega r, omega s minus omega r, everywhere there. Other than that, all are same, all are identical. I mean, you can see cosine, it was omega st, it is omega s minus omega t. The second term here, it was minus sine omega st, it is sine omega s minus omega t, omega rt, and so on. Okay, so I hope it's clear. So in both cases, actually, we are taking the relative speed, and that relative speed is actually appearing in the corresponding DQ0 transformation matrix. So nothing else. So that's why these two would be a little different. Okay, the TDQ0S and the TDQ0R, they won't be exactly the same, but they would be similar. The only difference lying in the fact of the relative speed. So with those two, TDQ0S and TDQ0R, now we can apply these TDQ0 transformation matrices and their inverses as well to the corresponding equations into the DQ axis flux linkage expression. We had the ABC flux linkage for stator. We had the ABC flux linkage. So those are present in equation 4. So this is lambda ABC. We want lambda DQ0. So what to do? Simply apply the parts transformation for the stator. That means the one given in equation 6a, this one. So if we use that, then we can easily transform the expression in 4 lambda ABC to the expression in 7a, which is lambda ds, lambda qs, and lambda 0s. That means lambda dq0 for the stator flux linkage. And ultimately, when you apply the suitable transformation matrix, you will get something like this that is present on the right hand side of equation 7a. So you can see that because of being a balanced system, you don't have any zero axis flux linkage. There is 0. All are 0 here. Okay. So in the 0 axis, lambda 0s is actually 0 plus all 0 over here. So in summary, we can say that lambda 0s would be 0 because it is a balanced system. That is quite natural. So what you will get, lambda ds is LSS IDS plus LM into IDR. So if I break it down, the expression of lambda ds, I would get LSS IDS plus LM IDR. So this part is for the stator d-axis current, and this part is for the rotor d-axis current. Okay, so along with the transformation for the flux linkage, what we also have to do, we also have to transform the corresponding currents, IDS. So here for the transformation, you would need to use TDQ0S because it is a stator quantity. The second one, however, is the rotor quantity. So you have to use TDQ0R. Okay, so you have to be a little careful while using the transformation matrices. Similarly, lambda QS would be LSS IQS plus LM IQR. Okay, so again, this should be TDQ0. You should use TDQ0S here, and for this one, you should use TDQ0R. So that's it. And the third one is lambda 0S equals to 0. For rotor, you again have, you can see all these are 0. So the rotor 0 axis flux linkage is all zeros because again the rotor quantities are balanced, 3-phase. Lambda dr is simply LM IDS plus LRR IDR. So again for this transformation and for this transformation, we have to use the TDQ0 TDQ0S, and for this one we have to use TDQ0R. That's it. And here during the derivation, probably you will come up with some quantities like this, LAA minus LAB for the stator inductances. For the rotor inductances, you might come up with this L capital AA minus L capital AB. So these are actually assumed to be LSS, and this is assumed to be LRR. And also this is the mutual one between small a is for stator, capital A is for rotor. So this is basically the mutual inductance between the stator coil and the rotor coil inductances. So LM 3/2 LAA. So just some notational simplification. Okay, so with these assumptions, we can easily write down equation 7A and 7B. So this is for the flux linkages. Remember, we also have to do the same for the voltage expressions. So in the next slide, we get that expression for the DQ axis. Now for the voltage expressions. So the voltage expressions were written in equation 2A up to 2C. This is for the stator. And in equation 3A up to 3C, that is for the rotor. So once we apply the Parks transformation for the voltage expressions, we can see that we have now, instead of VABC, we have VDS, VQS, and V0S. And there is the mutual coupling. So VDS would be some function of lambda QS, that is minus omega S lambda QS, and VQS would be some function of lambda DS. So there is mutual coupling between the voltage and the corresponding flux linkage. And there is no contribution of the flux linkage for the lambda 0S on V0S. However, the V0S is a function of the 0-axis stator current due to this voltage drop, RS I0S. And there is one additional time derivative term. And again, here you can clearly see that which of the transformation you should use. So this is a stator quantity, so you should go for TDQ0S. This is again a stator quantity, TDQ0S, and this is again a stator quantity. So all of these should be TDQ0S. You should use TDQ0S in your derivation. For the rotor, this is TDQ0R, and these all should be TDQ0R because these are rotor quantities. The only difference here lies in, let's say this is RS, this is RR, this is minus omega S, because that is the relative speed between the ABC frame and the stator, stator ABC frame and the DQ axis, DQ0 axis. And this one here, it should be the relative speed between the rotor actual speed, omega R, rotor frame, and the DQ axis frame. So this is omega S minus omega R. Okay, so after you apply all these transformation matrices and their inverses, you should get equation 8A and 8B as presented here. Okay, so once you get it, next job is to go for the apparent power expression. So the rotor apparent power is simply, as we used earlier, the generic expression, the rotor apparent power. Remember, the rotor apparent power means how much power you actually getting into the rotor through electromagnetic induction. Remember, we are only applying power because it is an induction machine. We are not applying any electrical input directly into our rotor body. This is induction machine. So what we are doing instead, we are supplying some power, electrical input, to the three-phase coils of the stator, and then we have, of course, have some air gap, and through the air gap, actually, the energy is being transmitted from the stator field coils, or from the stator magnetic field through electromagnetic induction. The energy is transferred to the rotor coils, and ultimately the rotor would get the torque. So the rotor would get some induced torque, electromagnetic torque, due to which the rotor would start to rotate. So there is some electromagnetic induction process. Now, how much power is actually available on the rotor shaft? That is an important quantity. Why? Because ultimately these rotor, this torque induced would go and it would actually run a mechanical load. Okay. So you need to know how much power is actually available, how much power is developed on the rotor itself. So from that power, after you deduct the mechanical losses, rotational losses, friction and windage losses, then ultimately you would get the final mechanical power available at the shaft for running this mechanical load ultimately. So this S rotor is actually the apparent power because you are applying electrical input. So that means that electrical input is ultimately coming into the rotor circuit, and how much power, apparent power, is available at the rotor shaft. Okay, so that is the apparent power, not the real power. Remember, that is the apparent power. And apparent power is simply, you can write VAIA plus VBIB plus VCIC. This is the three-phase apparent power. Sorry, there is a little mistake. All this should be capitals because we are using capital letters for representing the rotor power. So rotor quantities. So this is VAIA, VBIB, and VCIC. Okay, so all are caps. And in short, we can write these in the vector form, vector multiplication form. We can simply write it like VA, VB, VC transpose into IA, IB, IC. So that's it. So when you transpose it, simply it means it is VA, VB, VC multiplied by IA, IB, and IC. So that's it. So then what you have to do, because all quantities, we're actually bringing them to the DQ0 axis quantities. So this ABC frame and this ABC frame, you have to use the transformation matrices. And finally, you would get the voltage phasors in DQ0 frame. Remember, this is now in rotor frame. VDR, VQR, and V0R, these are in the rotor frame. IA, IB, IC, these are in rotor frame. IDR, IQR, and I0R. And in between, these are the matrices and the inverses that you need to use for properly completing the transformation from ABC rotor, VABC rotor, and IABC rotor. So VABC rotor is transformed into VDQ0 rotor multiplied by some transformation matrices. Appropriate transformation and transposition is required. Similarly, IA, IB, IC, for transforming it into from rotor quantities into the rotor ABC frame to rotor DQ0 frame, you need to pre-multiply this. So one is the post-multiplication, another one is the pre-multiplication. So this is pre-multiplication, this is post-multiplication. And in the stator, the synchronous machine topic, I have shown it elaborately how you can incorporate these matrices and how you can complete this calculation using the transformation matrices. And because both of these VABC rotor and IABC rotor, both of them are actually rotor quantities. So you can see clearly that this is the TDQ0 rotor, and this is also the TDQ0 rotor. So then if you use the actual expression of TDQ0R inverse and TDQ0R inverse here, this one is transposed, this is transposed, this is inverse. So when you when you multiply these 3 by 3 matrices, ultimately when you simplify, you should get this. Okay. After simplification, you should get this. So once you get this, you can see that there are 3 parts in the whole expression for S rotor. The first part, it is very clear that you can clearly see that it is something like IDR squared plus IQR squared multiplied by RR. So this is something like I square R, which is nothing but again the rotor copper loss. I square R, RR. So it is rotor copper loss. The first part is nothing but the rotor copper loss. The second part, you can see that this is lambda I, some lambda I minus some other lambda I multiplied by the slip speed. Okay, so we leave it for the time being. Come to the last part. The last part is IDR multiplied by the rate of change of flux linkage plus IQR into rate of change of flux linkage. Okay, so this part is basically purely associated with the dynamic time frame. So whenever your machine will be under dynamic time frame or the dynamic condition, the transient condition, these would be non-zero. However, if the system, your induction machine is running at steady state speed, okay, no dynamics, no transient, then this would become 0. So under steady state, this is 0. Under dynamic state, this is non-zero. Okay. The first term is the rotor copper loss. It is present always in the dynamic case or in the steady state case. Second term is also present in all the state or all the cases, be it the steady state or the dynamic state. So the first term already discussed. At steady state, what would happen? These dynamic terms, time with respect to time, this time derivatives would be 0. So let's say if we consider the rotor apparent power under steady state case, so we can cancel this out. Okay. Now, what kind of loss is this? Is it a mechanical loss or an electrical loss? The rotor copper loss, we can clearly see that this copper loss is purely a function of the rotor current. So this is an electrical loss. So the rotor copper loss is nothing but one sort of electrical power loss. It is not the mechanical loss. So that means after you provide your input power, okay, input power into the stator. So P in is stator. This goes to the stator minus the electrical losses. Electrical losses could be your core loss and your copper loss. So core loss is voltage dependent and copper loss is current dependent. So P electrical, this is the loss. So after you subtract this, where in the P electrical, within the P electrical, you can have P copper loss and P core loss. The resulting power would be your P, let's say P, we should say P, whatever P is available for transforming into mechanical power. Okay, so this is P, you can say P air gap. Okay, P air gap. Okay, so then in that case there would be a little difference because there is P stator copper loss and P rotor copper loss. So it shouldn't be totally P air gap. Rather, it should be P available. We can write it like this: P available for mechanical or P mechanical. Give it some name, P mechanical. And now, if you deduct P from P mechanical, if you deduct the mechanical loss, P mechanical loss, that would be your P output. So this is the final P output. Okay. So P mechanical, you can say some intermediate level of power before deducting the mechanical losses. So what are the mechanical losses? Mechanical losses could be P rotational losses. Okay. P friction and windage losses. Friction and windage losses. So these are the mechanical losses. Okay. So this is the final ultimate P output power. But we are actually looking at the rotor apparent power. Okay, the rotor apparent power. So in this case, the torque that is induced for getting the rotor apparent power is this one. So out of this one, actually, you would get the required torque, because you see lambda I, lambda QR IDR minus lambda DR IQR. So that means there is some interaction between the Q axis and D axis quantities. And if you deduct this loss, this is the electrical loss, this is the dynamic, this is the power present in the dynamic state. So in the steady state, you don't have to bother about this. So the remaining term is actually your the power which is available for induced torque, which is responsible for the induced torque. So this is your T electromagnetic. TE stands for electromagnetic torque. So for a p-pole machine, okay, if it is a two-pole machine, then this term will not appear. If it is a two-pole machine, you don't have to bother about this. But in general, the machine is a p-pole, okay, p number of poles. So in that case, you have to incorporate this additional p by 2 term, okay, with this. So this is a more generalized expression. For a p-pole machine, you simply multiply this 3 by 2 into p by 2 into this. So this is the torque. And when you multiply torque with the speed, you actually get the power, because P is torque into omega. This is the general expression for a general relationship between power and angular velocity and torque. Okay. So if you drop this, omega s minus omega r, because actually for this deviation in speed, you are getting this torque. So whenever for an induction machine, if somehow you can make forcefully omega r equal to omega s, then this would become 0. So you will not get any useful torque out of the machine. Okay. So the torque part is actually this part. 3 by 2 lambda QR IDR minus lambda DR IQR. And for p-pole machine, simply you multiply by an additional p by 2. However, for a two-pole machine, simply that would become 1, and you will be left with 3 by 2 and the remaining thing. Okay. So once this is done, then we have seen that actually there is some copper loss from the use from the electrical input. We have to deal with some copper losses. There is some component which is available only in the dynamic state, and there is some useful torque that is, of course, only present. That power out of this torque is only present whenever you have this speed deviation omega s minus omega r. So as long as omega s is greater than omega r, this is positive. That means the power would be taken from the supply. So as soon as omega r becomes greater than omega s, that would go into the generator mode of operation, and this term would be negative. So actually you will get some electromagnetic power output or electrical power output from your device that would make it run as an induction generator. So all these till now, we discussed about equation number 10. Till now, all these were actually in actual quantities, okay, not in per unitized form. So what we would do next, we would introduce some base value for transforming our actual quantities into the per unit quantities. Okay. So, and all of us, we should know what is the benefit of getting the representation in per unit form. Okay. So that is the whole thing. So the per unit representation, of course, we have two separate circuits, electrically separate but magnetically coupled. So we have stator quantities, some stator quantities and some rotor quantities. But for simplicity, we can assume the same base quantities for both these circuits, stator coil circuits and rotor coil circuits. So let's start with the base quantities. We pick a base voltage, and the base voltage is taken as the peak value of the rated phase voltage. Now there could be other variants at this point that you could choose. Here what they have chosen, let's say if it is VA, VB and VC, so they are choosing peak value of the rated phase voltage. That means VAN. If this is your, let's say three of the phases, phase A, phase B and phase C. So there should be some, and this is Y connected, so there should be some neutral point. So in that case, they are considering that this voltage VAN, that is the phase voltage, or VBN or VCN, the peak value of the phase voltage. Otherwise, you could also take VAB, that is the line to line voltage. You could also take VAN RMS or VAB RMS. So there are different possibilities, okay? But in this case, in the book, they have taken the peak value of the rated phase voltage as the base quantities, but there are some other possibilities that you could go for. Similarly, the base current is taken as the peak value of the rated current, that is ampere. The frequency base is the rated frequency in hertz. So these are the base quantities. And once you have the base quantities set for voltage, current, and frequency, you can easily manipulate the base quantities for the other remaining quantities, like the Z base is simply V base by I base, and the unit V by I, volt per ampere, that is ohm. Omega base, angular base frequency, would be depending on purely on the F base and multiplied by twice pi. And the unit should be, because the unit of F is in hertz, so the omega base unit would be electrical radian per second. L base, simply Z base by omega base, because L into omega is actually your Z. Okay. And accordingly, you can calculate L base equals to Z base into omega base. Then lambda base, again, V and lambda could be related with the help of the omega. So lambda base would be V base by omega base. S base, because of your choice of K1 and K2, you can clearly see that in the expression of S. So here is an observation. So we chose actually 3/2 in our transformation matrices. Okay, where is that? Okay, in slide number 10. So you can see it is 2/3 half. So because of this choice of K1 and K2, this set of choice, we got an additional 3/2 present in our torque expression or the S rotor expression. So that's why while we are calculating the base power, apparent power, we are intentionally introducing or choosing this additional 3/2 term over here along with V and I. So it would be 3/2 V base I base. And again, torque base is represented also with the help of the pole pair or number of poles present in the system. And because it is lambda I, you can clearly see the lambda I term will give you the torque. The lambda I term will give you the torque, TE, where you have lambda multiplied by I. Some form of multiplication form of lambda into I, that would be your torque. And when you multiply torque by the angular speed, then you will get the power, electrical power. So lambda I is basically the unit for the base torque. So if the lambda base, I base, the unit for torque is Newton meter, and this 3/2 comes again because of the presence of 3/2 in the torque expression, and P/2 comes because of the variation in the number of poles of machines from one to the other. And we continue with the per unit representation. So we have now VDS, VQS. So all these are now the DQ in the DQ frame. Okay. So now this one was in the ABC frame. So this was done in the ABC frame, VABC, IABC, SABC. So now in the DQ frame, what we do is simply use the VDS small, V small DS. It is in the DQ frame. So this is D frame, this is Q frame, but actual, all these are actual. So what we are doing, we are simply dividing it by the voltage base, because the numerator is voltage, and the resulting V, capital VDS, is the per unit representation. So the small v is used for actual quantity representation. The capital V's are used for the per unit representation. Similarly, IDS, IQS, IDR, IQR, and so on. Psi DS, Psi QS are the per unit flux linkage in the D axis stator, per unit flux linkage in the Q axis stator. These are two are for the rotors, and similarly for the stator coil reactance, inductive reactance, rotor coil inductive reactance, the mutual reactance, the stator resistance, the rotor resistance, the electromagnetic torque, and the rotor speed in per unit. So the rotor speed is per unit is simply the actual rotor speed omega r divided by the speed base. And interestingly, it is also related with the slip. So omega r per unit equals to omega r by omega base equals to 1 minus s. We can also get it from this slide. Okay, so from this slide, you can also relate that, because omega s is the synchronous speed, remember. Omega s is the synchronous speed, and that is also taken as the omega base. So clearly, S is nothing but omega base minus omega r by omega base. So we can also write S omega base. So omega r equals omega base minus S into omega base. And then omega r is omega base into 1 minus S. So omega r over omega base is 1 minus S, where omega r by omega base is nothing but omega r per unit is equals to 1 minus. So this is how you can get the relationship done. You can prove this relationship. Omega r per unit equals to omega r by omega base equals to 1 minus S. Okay, so these are some of the per unit representation in the DQ axis. So in the per unit DQ frame, okay. So now there are two things. One is the ABC frame is transformed into DQ frame. Another one is all the voltage equations and flux linkage equations all are now in per unitized form. So once that is done, then you will get that VDS is RS IDS minus Psi QS plus 1 upon omega base d Psi ds over dt, and VQS is RS IQS plus Psi ds plus 1 upon omega base d Psi QS over dt. So these things are actually obtained from this equation 8a. Okay, so these are in actual quantities. Now you transfer. So you see there's small symbols, small v ds, small v qs. So from 8a, what we do, this is in actual form. Voltages are in actual quantities. The resistances, stator resistances are in actual quantities. The currents are in actual quantities. Flux linkages are in actual quantities. So when we take the per unitized representation, they become capital, and there are some changes. You see the omega base is coming in addition to the one present in the previous equation for the voltage. So in 8a, you don't see any omega base. Once you take the per unitization, then in equation 11a and 11b, you will get the VDS and VQS, and there will be some 1 upon omega base. So all symbols are in capitals, means all are actually in per unitized form. Similarly, for the rotor voltage VDR and VQR, we can take help of equation 8b. This is in actual form, and in per unit form, you should get this 11C and 11D. Then the flux linkage, similarly, psi ds, psi qs, psi dr, and psi qr. These are coming from the lambda expressions, which are present in equation 7a. So from 7a, you will get the lambda d, lambda q, you will get psi d and psi q. From 7b, you will get psi dr and psi qr in per unit form. So from 7a and 7b, you will get these four expressions. Okay, so I think we can stop here today, and inshallah in the next class we will be continuing from the next slide. So what we would do next, we would go for some sort of simplifications, as we did for the case of synchronous machine. And once we go through some simplifications, probably we would be in a better position to represent the system in the state space form. Okay, so that's it for today. So please go through the lecture, and if you have any queries associated with this, please prepare your questions accordingly, and we can take several minutes at the beginning of our next lecture, so that if you have any query, we can clarify those issues before we proceed further in the next class, inshallah. So, okay, so till then, stay safe and stay good. Assalamu alaikum wa rahmatullah.